Hello and welcome to the lecture 6 of the course Microelectronics Lab. In this module, we are going to give you a lab demo of high power pulse and TLP characterization unit. Broadly, we will be covering the TLP setup and its integration with probe station. We will talk about application of high power pulse and TLP characterization in ESD and ESD related testing. We will then come to the theory of the TLP and the high power pulse setup. We will describe the setup including pulse generator, pulse width extender, oscilloscope, the integration, calibration and all the other RF pulse measurement related issues.
Hi everyone, my name is Rajat Sinha, and on this sunny morning in the Bangalore, we will be talking about a very important and intriguing characterization technique for microelectronic devices. So that technique is called TLP characterization, and over the period of this video I will talk about more why is it important and why is it intriguing as well. So I hope you will enjoy this video, and while you are seeing this video, take care of yourself. So there is a pandemic raging outside as well, so yeah, use this time and take care of yourself. So before I go into the details of why this technique is important, and I'll tell you more about this technique as well, let me take a couple of minutes and discuss what this technique does and why I use the word important for this technique. So basically, if you're familiar with microelectronic devices, you would know that there are a lot of problems that come when you fabricate devices, when you make these chips. And one of the major problems that comes in microelectronic device fabrication is electrostatic discharge. Now, electrostatic discharge, on its very basic, is basically a charge transfer taking place from one body to another when there is a potential difference between the two bodies. So the best example of this would be lightning strike. So when there is a potential difference between two clouds and there is charge stored on one, there is a charge transfer that takes place between these two clouds. Now lightning strike in itself is not an economic disaster, and it does not affect our daily life in a lot of ways. In microelectronic devices, however, ESD can cause a lot of damage as well. So for example, in 2010, more than $1 billion were lost to this problem alone in microelectronic fabrication. So that's why this technique becomes even more important, because it helps us resolve one of the major problems in microelectronic industry. So ESD is basically, as I said, charge transfer from one body to another, and that in microelectronic cases involves a very high voltage amplitude, a very high current, and a very short time period. So the time periods that then we talk about are in the range of 100 nanoseconds or so. So as human beings, you don't feel charge transfer taking place in your body all the time, but in microelectronic devices, then it becomes very important. It is also important in the case when we are talking about new technology developments. So for example, you see a lot of technology development taking place these days in terms of photonics, MEMS, surface acoustic wave sensors and all that thing, flexible electronics as well. So there it's important to understand ESD behavior upfront. It's important to understand what problems could come up when you develop technology, and then you have to proactively find solutions. So if you don't find solution proactively, you have a lot of problem at your hands once the technology is developed, and then it becomes even more difficult and economically inviable to solve that problem. So that's why ESD is a major reliability issue in microelectronic industry. A semiconductor chip development involves a lot of different steps. So first it involves technology development from the fabrication point of view. So basically a fab somewhere in the world, say anywhere, somewhere in the world, say TSMC is in Taiwan, develops a new technology, they make new fabrication, they make new devices. Now this device fabrication is based upon the inputs that they get from their own design teams for the requirements that they want. So say for example, if I wanted to fabricate a 100 volt MOSFET, I would send a lot of inputs to my fabrication team, and they would then fabricate the devices on that. Once your device is fabricated, you have to understand whether it's performing up to the mark or not, and if it is facing some different problems. So you test for different reliability issues. ESD is one of them. You also test for other reliability issues, and I think some of my friends will talk about these techniques in other videos as well. So I'd leave it up to them. Yeah, so ESD is one of the issues that you have to understand and realize at the very starting point of a technology development. Once the technology is developed, you have the devices in your hand, you have some MOSFETs and SCRs, resistors, capacitors all in your hand. everything is fine. You then have to make circuits out of them, right? MOSFET in alone is not a useful component for everyday consumer. So then you have to test them on their systems as well. So say for example, if I were to make this monitor, I would fabricate everything, then I would assemble everything, and then I would test the system all over again for ESD reliability. So basically ESD measurements have to be done at two different stages. One is at device fabrication, and then when the whole system is ready as well. So I was talking about damages caused by ESD and $1 billion involved. So what I'm showing here are some of the major damage photos of microelectronic devices over a period of time. So as you can see, so they basically, in a nutshell, these are different contacts that I'm showing here. This is also a different contact. So all these planar areas that you see are metals in different places, and then you have these gate contacts. Then you have somewhere, gate contact here as well. So then you have ESD damages which lead to damage of the active area. It could lead to the damage of the source drain area, or it could lead to the damage of gate oxides as well. So this is a simple schematic to show where the ESD becomes a problem. So now ESD becomes a problem whenever the system interacts with something else. So say for example, if you were to touch a USB port, charge that is stored inside you would then get transferred to the whole USB port area, the microelectronics involved with it. And so you have ESD problems in mostly two areas. One is the output-input ports, and the second in the power domains. So basically the power that is being supplied to the whole microelectronic circuits also have this ESD issues as well. So these are the two major domains where you see a lot of ESD problems. The question would then come, how do you even measure ESD? It's a random phenomena which charge transport from one place to another, and it's very difficult to actually know when it's going to happen in a system once it is in the hands of a consumer. So then the question would come up, how do you even measure it? How do you even understand it? So based on a lot of mathematical data, based on a lot of modeling, and a lot of physical understanding as well. So you basically summarize ESD issues in form of three different models. So these models are human body model, charge device model, and machine model. A human body model is basically a simulation where you think that the charge is being transferred to a device under test from a human body. So then you have these different components. So you basically model it as a form of circuit, and you have these different components R and C, and their values are then determined based on empirical data. As an industry standard, what we use is a resistor of 1.5 kilo ohm and a capacitor of 100 picofarad along with a high voltage source. Charge device model is then a model of ESD where we think that the charge of our device is coming from the another device. So basically, instead of a human body, it's another charged microelectronic component that is causing the ESD issues. So in that case, you have a very smaller R substrate, R component of the circuit, and the capacitance is much higher. Another model is then machine model. Machine model is when, say, if you were in an automated factory somewhere and your robots are touching your microelectronic devices. So in that case, a charge could also come from these robots to your microelectronic device, and that will also cause ESD issues. So machine model is the third model which we use as a ESD qualification for different components, MOSFETs, SCRs, etc. And so these are device level components. Then there is a system level component as well. So for example, again, I'll use the monitor as an example. If I were to qualify this monitor for ESD reliability, then there is a system level component called IEC 61042. I don't think I have that information here. Anyway, you can always Google it. So IEC 61042 then lays down the characteristics and the parameters that have to be qualified for ESD reliability in bigger systems. So HBM, CDM, and MM follow the component level or device level testing, and this IEC then follows a system level testing. So this is more about ESD in a very nutshell. It's a very nutshell information, and you can always go through a lot of literature and books on this. And I would suggest, if you have interest, I would suggest that you go through them. It's an interesting topic, but I'll deal with it in this much detail only. So yeah, you can always ask me questions as well. So now that we have discussed what ESD is and how it causes the damages in electronics industry, we'll start to take a more detailed look at the characterization technique that we are going to talk about today. So this is basically a probe station that is used for the measurements of any component involved. So this the outer covering that you see is called a Faraday cage. It's used to protect any device that is inside from the electromagnetic waves that you see in the ambient, right? Light is also an electromagnetic wave. So yeah, you need to protect all your devices from them. Then you'll see that this whole probe station is then standing on this kind of a cushion. Now the reason I'm calling it a cushion is because it is actually a cushion filled with air. So whenever you push this whole assembly down, the devices will not experience any turbulence, because then you are sitting on a chamber of air. So then this is the major component of the probe station. This whole assembly here is a microscope that is used to view your devices under test. This is called a chuck. A chuck is where your component rests. You'll keep the component here, and then you can move it around as well wherever you want. And this chuck right here is an electrical chuck. So basically, if you want to apply any electrical signal on the back of the device, say any substrate bias or something, that you can apply it through this device, through this chuck. These hairs are then called probe arms. So whenever you have your device under test, you have to make an electrical contact with it as well, right? You have to make electrical contact with the source drain and the gate contacts. So these probe arms are then used to make the contact with the device under test through these wires, through different assembly of the components that you are going to use. Another thing that I can mention is that this microscope is then movable. You can actually move it in the Z direction. You can move this chuck in the XY direction, and you can move the whole assembly to whatever configuration you like. The devices that are rested here are then on the vacuum as well. So basically, you have these small holes here on the chuck, which make sure that your device does not move along in the measurements. So when it will not move along whenever you don't want it to move along. So that's why you have these vacuums as well. So at this point in the video, we have already talked about ESD issues, why these issues are important to understand in a microelectronic circuit, and then we have taken a very brief look at the probe station that is involved in measurements. And I think one of my friends will talk more about the probe station, and so that video would be very important if you don't have an exposure to a probe station as well. Now we'll talk more about TLP characterization, and I'll talk more about the theoretical basis of the whole characterization technique, and then I'll show you some components, some major components that are involved in this characterization. So now there are multiple characterization techniques that involve that get involved in the microelectronic reliability. So one is called DC reliability tests. So basically, in a DC reliability measurements, you apply a DC signal to the different contacts, and you can choose the contacts appropriately as you want. Then there is something called pulse characterization. A pulse characterization that involves applying pulse voltage signals to the device under test, again to different contacts. Now there are some important considerations when you talk about pulse characterization techniques over a DC characterization technique. So one is, as you can understand, a pulse characterization technique involves a lot of waveforms. So you need to have a good control over the waveforms as well. And if you wanted to say apply a square wave and it's coming out at a triangular wave, then your whole measurement is ruined. So you need to have a good control over the whole waveform that is being applied. You need to have a good control about the amplitude, and you need to be very careful about the on-off times, because depending on these on-off times will depend how much heating you're applying to the signal and how much your device is on and off, and all these different non-ideal effects would then get related to the on-off times. You also need to understand that in a pulse characterization technique, as you can think, you will also need to do the calibration of a system. The calibration is important because whenever you involve any wires around, you also involve a lot of different parasitics. So these wires also then have capacitances, resistors, and everything, and they can then play around with your waveform if you don't calibrate the system well. And in this video today, we'll talk in some detail about the calibration of the TLP setup as well. Now the TLP setup in general is a little more sophisticated than any pulse setup, because then you are dealing with even shorter pulse time periods. You're talking about time periods in the range of a few nanoseconds. And you're talking about the voltage amplitudes that are in excess of a few hundred volts and can go up to 2 kilovolt if you want. So that's very higher as compared to any other pulse characterization technique. So the TLP characterization then is a bit more involved. So the first thing that I'll show you is what and how TLP pulses are generated. So this here setup, this here is a pulse width generator and extender. Now what is inside the generator is somewhat of an IP, so I would not give you too much information about it, but in a very basic way, it's an RC circuit, it's a transmission line, and you then charge these capacitors and transmission lines, and then whenever you want, you can actually discharge these the transmission lines inside it, and you can apply the voltage waveforms and voltage amplitudes, whatever you want. Pulse width extender is then necessary because your generator in its default state cannot apply on time periods of more than 100 nanoseconds. So this pulse width extender then goes up, takes the whole setup up to 1.5 microseconds, and that's why it becomes important, because then you have to do measurements for a longer time. You actually use this pulse width extender as well. These two components are connected on the back side through a common connection. So basically, the communication line between the two instruments is very well, and they can actually synergize between themselves as to who has to get involved at what time period. So this is how the pulse width is generated. Another important component here is an oscilloscope. So whenever you're talking about waveforms, you would also want to capture these waveforms. You can capture some data, but it's always more intuitive and it's better to capture the whole waveforms if you can. And that's where oscilloscope comes into picture. Whatever I'm going to apply to the device under test, and I'll show you in another video how these measurements are done. Whatever you apply, whether it's current or voltage, will also get captured in this digital phosphor oscilloscope here. So the oscilloscope that we use has a very high sampling rate. It's around 25 gigasamples per second. And there are different variants of the oscilloscopes that are available in the market. So these oscilloscopes are then used to capture the different waveforms, applied, captured, measured, whatever you want to capture, you can actually capture in this. And there are a couple of SMUs involved as well. These SMUs are then important if you want to apply a DC bias to your device under test while also applying the pulse voltage. So say for example, if I were to keep a gate grounded during the measurement and I were to apply these pulses at the drain contact, so I can then connect the whole assembly in one shot by by connecting the gate to an SMU, by source drain to the TLP setup here, and then I'll measure everything through this oscilloscope. So that's one of the some of the major components of a TLP setup. So now what I'll do is I'll talk more about the whole setup. I'll tell you what are the different things involved and what are the different connections involved in the whole TLP setup. So initially we were talking about a TLP generator. Now in this setup, this HPPI TLP 410 is the TLP generator that we are using. Now this generator, as I said, was the one that creates the high frequency, high wave pulses, high amplitude pulses, and then it applies these pulses to different devices under test through a whole assembly. So this is then connected to this 3011, which is a pulse width extender, and I told you the importance of pulse width extender in the circuit as well. So this 4010 is the TLP generator, and it is connected to the pulse width extender, which is 3011 here. So this pulse width, the importance of this pulse width extender I've already told you, and they are connected through an internal circuitry. So then this pulse width generator is then connected to a switch. Now I'll talk about the switch in more detail when I show you the component as well. Through a transmission line. The importance of the transmission line and why we are using a transmission line everywhere here is that a transmission line has a fixed impedance. Now you don't want a lot of impedance mismatch in the whole circuit, because as there will be more and more impedance mismatches at different points, there would be both reflected and incident waves. And say for example, if I were to use a random impedance here, that random impedance would then lead to a lot of reflected waves, which I don't want, one. And then secondly, I will not be able to measure how much of the incident wave is then getting reflected because of the impedance of the transmission line. So everywhere in this whole setup, the impedance is the impedance of all the different lines is calibrated to 50 ohm, and a very set important transmission line is then used, and I'll show you the transmission line as well. So so that's the importance of using a 50 ohm transmission line in the whole setup. Now this TLP generator is then connected to a switch. This switch is important because it switches the whole measurement setup between different measurements that are going to take place. Now as I told you, the switch is going to is going to alternate between different measurement setups. So at one point of time, so say for example, if you were to measure the device and then you wanted to check the health of the device after every pulse, by applying a very low voltage bias, you would also need a SMU here, and this switch then alternates between this pulse generator and the SMU here. So and then once it alternates, it then passes on the signal to the device under test. This signal is then passed through a current sensor. This current sensor is basically a current transformer, then measures this reflected in the incident waves and sends its output to the oscilloscope, which then captures the current waveforms, and the other output from this current sensor then goes to the device under test. Now TLP pulse generator, TLP is at 4 probe measurement. So basically in a 4 probe measurement you have different probes for current and different probes for voltages. So this is the current waveforms. Now another set of waveforms get captured from another set of tips. Now these tips are then a voltage divider circuit here. These voltage divider circuits then capture the voltage across the device under test, and then they send the whole signal to the pulse sense here. So, and then this pulse sense then goes to the channel 3 of the oscilloscope. So basically when you apply a voltage pulse through a TLP generator, you have this pulse waves traveling through the oscilloscope, traveling through the transmission line to the switch here. This switch then alternates between the SMU and the pulse. So say for example, at one point of time it will apply a pulse, then immediately after the pulse it will apply a DC SMU signal just to check whether the device is okay or not. So yeah, so then the pulse will then pass through the current sensor here, which will measure the current voltage current waveform of the device under test. This will then get applied to the device under test. Another set of probe tips here, which consist of a resistor divider network, will send the output to the switch again. Now this switch through its pulse sense terminal will then get connected to an oscilloscope channel, which will measure the voltage waveform of the device under test. So this is the whole circuitry of what is involved in the TLP setup. Now I was talking about this SMU as well. As I told you, this is called leakage measurement. Leakage measurement is important because you would like to see how your device is getting shifted. So say for example, when the device was brand new, at a voltage application of 1 volt, it was passing say 1 nanoamperes of current. You would like to see as to how the device current is shifting as you apply different stresses. Okay, so the stress that we apply in a TLP measurement gradually increases from 0 to whatever desired level you want, say for example 200. So from going to 0 to 200, this SMU will then measure the current at 1 voltage level at different pulse voltage levels. So say for example it will measure at 0, then it will measure at 5, it will measure at 10, and see how the device is gradually shifting. So that's why this test becomes very important as well. So some of the major components that are then involved in the whole setup, as you can see, are these: generator and the pulse width extenders, oscilloscope, this switch here. Now this switch becomes important because this pulse that you're applying is a 100 nanosecond or say even lower pulse. The lowest that we can go is a few nanoseconds, 1 nanosecond. And then this switch has to switch on faster, as fast as possible, because it has also to alternate between them, between these measurements. So then this switch becomes very important. The current sensor is very important, because if your current sensor is faulty or if it's not up to the mark, you'll not be able to measure any voltage current waveforms. Then these transmission lines become important. Yeah, and then you have these attenuators here and the oscilloscope inputs. Now using these attenuators is pretty common, however it's not necessary. So the reason why we use these attenuators is because these oscilloscopes can only take a voltage input of 5 volts, and if your input is going to be higher than that, you would not have to use these attenuators. And we'll take these attenuators into consideration when we start talking about calibration as well. So when I was talking about the whole TLP circuit and I was discussing the schematic of the whole setup, I was talking about different components that are very important. Now the first one that I was talking about is a transmission line. As I told you, a transmission line has a characteristic impedance of 50 ohm and that's important because it reduces the mismatch at different points in the whole setup. So now this here is a transmission line that we use. This transmission line has an inside signal pin here and the outside shielding that serves as the ground. So these are all SMA cables. The good thing about these cables is that they have a very high dielectric breakdown. So basically, if you apply a very high signal voltage to the inside pin, the whole cable would not get damaged very easily. And secondly, it has a 50 ohm transmission characteristic impedance. Now you can see that I've kept all the transmission lines here in a circular fashion. Now the reason that I've kept this whole transmission line in such a fashion is you don't want kinks or any damage to the transmission line anywhere. So if you remember your concept of transmission lines, the components that we talk about, RC components of a transmission line, are distributed in nature. However, if there was to be a kink or a geometrical damage somewhere in the transmission line, the distributed resistance and capacitance at that point of the cable would become different from 50 ohm, and in that case that point would start reflecting different waves and you would not be able to measure the whole signal properly. So that's why it's very important to keep these transmission lines in a very proper fashion and avoid any kind of geometrical damage to them. The second component that I was talking about is a switch here. Now I told you the switch is important because it alternates between SMU and the TLP measurements. It also has a pulse sense line which then measures the current waveform, the voltage waveforms as well. Now the reason that the pulse sense measures the current waveform as well. So you basically have a transmission line coming here to the pulse force coming from the TLP generator. This pulse line is then passed through the device under test through these terminals, pulse force and leakage. Now the terminal leakage has the connection going for the leakage measurement test. Okay, and the pulse force has the pulse line going here. So basically, your TLP probes will be connected through this set. They will actually be connected to both the sets. Yeah. So you have these two outputs going from the switch. Now the third is this input here, pulse sense. So the voltage divider network will send its signal to the pulse sense terminal here, and you will measure it through the oscilloscope through this output terminal, DUT pulse sense. This output terminal will then go to the oscilloscope. Now this switch is important because it has to respond to a very high frequency signal, and it's a mechanical reed switch that we use. It also has a very high reliability because you don't want your switch to get damaged. So basically it has a very high bandwidth, and it also has a very high breakdown voltage. The third component that I'll talk about is a current sensor. Now current sensor in its very essence is basically a current transformer. So basically you will have a pulse signal coming from the switch and the TLP generator to the current sensor. It will then get transmitted to the device under test, and the response of the device under test will then come to your current sensor, which will then be transmitted to the oscilloscope. So basically you will apply a voltage signal here to the input, to the input terminal here. The output terminal will then go to the device under test, and the sensor output will be then measured here, and the output signal, output voltage waveform will then go through this terminal to the oscilloscope. So yeah, so the current sensor has some parameters that are important. The one is bandwidth. So every current sensor also has a bandwidth. It can only measure up to that much frequency. So for example, this current sensor has a bandwidth of around 3 gigahertz. Then the second thing is the sensitivity of a current sensor. So say for example, if I was to apply a 1 volt signal, 1 ampere of current, say for example, the oscilloscope in itself cannot measure current, right? So it can only measure voltages. So the oscilloscope will then receive the input from output from this current sensor in a form of a voltage pulse, and that will depend on the sensitivity of the current sensor. So for example, this current sensor has a sensitivity of 5 volts per 1 volt per ampere. 0.5 volts per ampere. So basically for every ampere of current, it will transmit a 0.5 voltage to the oscilloscope. We also have other current sensors which have a higher sensitivity. So say for example, another current sensor that we have has a sensitivity of 5 volts per ampere. So that means it's a better current sensor in terms of measurement. That's because even your TLP setup has a lower limit compared for the current measurements. So say for example, if the device current is less than 100 microamperes, you would not be able to measure that using the whole setup. So the more sensitive your current sensor is, the better lower current measurements you will be able to do. So this is one current sensor that we use. As I said, there are a couple of others as well, and they follow the same patterns. They have all three connections, 3 ports coming, one from the TLP, another to the device, and one going from the device to the oscilloscope. So the third component that I'm showing you here is a tri-X connector. The reason that I'm calling it a tri-X is because it has 3 different signals that can carry. So the inside pin that you can see here actually carries the signal voltage or the signal that you are applying to the device. The outer shielding that you can see is a ground signal, and the third shielding that you see here then actually is another ground. It also protects the signal inside from any electromagnetic radiations from the ambient, and it also provides an external ground to your devices as well. The fourth component that I'm showing you here, is called a tri-X connector. The reason that I'm calling it as a tri-X is because it has three different signal carrying capacity. Now, that's the best. Yeah. So the first pin that you see here in the inside is called a signal pin. The outer shielding, the second outer shielding here that you see is called a guard ring. The guard ring is important because it protects your signal from any external noise. And the third outer shielding is a ground signal. So basically you have a signal, you have a protection guard ring, and then you have an outer ground as well. Yeah. The fifth component that I'm showing you here is an attenuator. So I was telling you about the attenuators at the input of the oscilloscope. Now these attenuators are passive components. So basically they don't actually consume any power of their own. Yeah. So basically these attenuators are these high frequency attenuators that we use because they have to attenuate a very high frequency signal. And these attenuators comes in different specifications, and their specifications are not voltage to voltage, they are decibels. And I'll talk about the ratings of different attenuators in the second video as well, and how these attenuators then impact the calibration setup that we use. So basically their purpose is to actually attenuate the signal coming at the oscilloscope to less than of what oscilloscope can actually handle. So an oscilloscope can handle at its input only 5 volts of signal. So the fifth component that I'm showing you here is called an attenuator. Now the importance of attenuator, I highlighted the importance of attenuators when I was talking about the TLP setup and I was showing you the diagram. These attenuators are connected to the input of the oscilloscope. Now they are connected because your oscilloscope inputs can only handle a certain voltage range. So say for example, our oscilloscope can only handle up to 5 volts at its input. And then when you are applying a signal that is very high in voltage, you need to attenuate the whole signal to under that level. Now these attenuators are passive components, so they don't consume any power of their own, and their ratings are in decibels. So they are dependent upon the power of the signal and the power output through the attenuator. That's why it's in decibels, and I'll talk more about how these attenuators impact the whole calibration setup when I talk about the calibration in more detail. However, as I said, you have to take care of these attenuators during the calibration processes because they directly impact the measurement that you're going to do. So the attenuators that we use generally have a rating of 10 decibel or 20 decibel. However, attenuators with a higher decibel rating or a lower decibel ratings are also available, and it's a matter of preference as well, or the signal that you're applying. So this is the fifth component, attenuator. The next component that I'm showing you here is a probe tip. Now when you have the whole setup in place and your device is also ready to measure, the connection to the device is then done through a set of probe tips. These probe tips are electrical conductors. So you can see a couple of wires here, thin 2 signal wires here. Now we are using so as I told you, TLP in itself is a 4 probe measurement. So it will involve 2 set of probes at both the contacts, source and drain, or any set of contacts that you want to use. So yeah, so it's a 4 probe measurement, and these 4 probes will land on 2 different set of contacts. So yeah, so you will have the signal contact of both the voltage and the current probe, and I'll discuss this in more detail when I do the measurements, and I think that will become clearer then. So your signal and the signal of both the current and the voltage probes will land on one probe, one contact of the device, and the ground of both the signal, both the pins, the current as well as the voltage channel, will then land on the other contact. That contact is grounded. So this is a typical probe tip that I am showing you here. You can easily see the two. I hope you can see these two signal lines here. One of them is a ground and one of them is a signal line. And how the way to know is through the specification of the probe tip. Now, when you see this whole set of numbers that you have, this set of numbers actually specify a lot of information about the probe tips. Now, some of it is necessary, and I'll talk to it about right now. So, for example, the 10 here is the model 10. In our measurements, we use the model 10 probe tips from GGB. The second set of numbers 50 here is the impedance of the probe. Now, every probe tip also has a certain impedance inside it, and if you remember, I was talking about a voltage divider network composed of resistors. Now, that voltage divider network is also present inside a set of probe tips. So, you don't actually have an explicit voltage divider network. So this probe tip has an impedance of 50 ohm. Then the 125 here is a thickness of the probe wires that you can see. So the two wires that we have, they have a diameter of 125 microns. W here is the material that they are made of. So there's a periodic table element that has the name Wolfram, and I think if you guessed it by now, it's tungsten. So these tips are then made of tungsten. There are other tips that come that are fabricated in molybdenum and gold as well. The importance of tungsten is that it has a very high temperature reliability, so it will not get damaged that easily. The 2 here is the number of pins that you have. So I told you, right, that they have 2 pins here. One is for signal and one is for the ground. The R here signifies the which of the 2 pins is actually a ground. So when you are going to look at this probe tip directly face to face, so for example, the pins would be facing you and you would be facing the pins. Your right hand side would the pin on your right hand side would be the pin that is actually ground. So the other pin would be signal. So that is something very important you have to take care. Many a times in the starting days we have made mistakes as to which pin was signal and which pin was ground, and you see very spurious results in that case. So both the grounds and both the signals have to go on single contact pad. So both the signals will go to one contact pad and both the grounds have to go to one contact pad. Finally, the 100 here is the pitch of the probe tip. What is the pitch? So basically, these two probe tips, probe wires, also have a certain distance between them. Now this distance is 100 microns. So what it does is, basically you cannot measure devices where the contact pads are less than 100 microns. So say for example, if I were to fabricate a 2D material device where the contact pads are closer than 100 micron and they are say closer, let's say they're far apart only by 50 micron, you would not be able to measure those devices through this probe tip. Now in such a case, we actually have a certain set of probe tips that has a flexible distance between the two wires, and I'll show you those probe tips when I do the measurements as well. But this set of probe tip has a 100 micron distance between the two probe wires. So that's all about the specification of the probe tips. Some important things that you have to take care while measuring, while using these probe tips is, one, as you can see, these probe wires are very thin. It's only 125 micron thick. So obviously you will have to be very careful when handling the probe wires. And I cannot tell you how many probe tips you have damaged over the years just because of a bit of a careless handling on the user part. So that's one thing, you have to be very careful. Every probe tip also has a power rating. So basically, you cannot apply a very high power more than the power rating of this probe tip. Now, in general cases, the power rating of this probe tip is pretty high for all the ESD measurements, but it's always a good practice to check what the rating of this probe tip is before you start the measurement. Now that I've talked about probe tips already, there's another, so the probe tips, as you can think, probe tips are not hanging, right? They're also connected to the whole setup through a set of probe arms. Now this is one of the probe arms that we use in our measurements. and we have more like this. So basically what you do is you connect the probe tips here at the end of the probe arm, okay, and then this goes to the device under test somewhere, say here. This probe arm then can move into different directions. It's possible to move these probe arms in X, Y, Z directions through different levers, different controls here, and you can move it to whatever desired height you want. It's always a good idea to keep these probe arms a little higher when the device measurement is not going on. Yeah. So another important thing that we have in our probe arms is, so when you're doing a TLP measurement, now I told you, right, the probe tips, the probe wires of the probe tips are also connected to each other. Now as you can think, when you're doing a measurement, it's important that those probe wires are also in the same plane, or at least in the same plane as the contacts that they're going to make contact with. So if your probe arms, probe wires are in different planes, you would not be able to make the contact with the device easily, because one of your probe wire would be touching the device, the other would not be. So it's important to bring them into the planes that you want them to be in. And then for this reason, there's another control that we have in these probe arms. So this is called a theta contact, theta control. So basically what it does is, say for example, if your probe tip is skewed on one side, you can actually control this and bring the probe tips, probe wires to the same plane. So this is a very typical probe arm that we use in our measurements. We have a set of another probe arms as well with a little different configuration for SMU measurements. But yeah, for TLP this is the typical probe arm that we use. Yeah. So the next component that I'm going to show you is called a high impedance transformer. So I was telling you that all the transmission lines and all the components that we use have a 50 ohm characteristic impedance. Now sometimes you would want the whole TLP setup to have a higher impedance than 50 ohms. So in that case, these high impedance transformers then come into play. So what happens is, you connect these high impedance transformers immediately after the switch that I've shown you before, and this transformer then switches the impedance of the whole setup from a 50 ohm setup to 526 ohm setup. So basically then you are using a TLP transmission setup that has a characteristic impedance of 526 ohm. Now this transformer also has a frequency rating and a high power rating as well, and that you'll have to be mindful of when you're doing these measurements. However, it's important when you are doing some measurements where your device behavior is not getting captured properly. So say for example, this happens in devices where there's a snapback and you want to capture the intricate details of that snapback, and that's where you use these high impedance transformers. Now the final component that I'm going to show you is called a calibration substrate. Now I was talking about the importance of calibration as a pulse setup and how it's even more important in a TLP setup where you are dealing with very high frequencies. So you need to do a different calibration steps, and I'll talk about these calibration steps now. So basically there are 4 calibration steps involved in a TLP setup. Now these calibrations are important because, one, your voltage and current channel may, because of different reasons, have a time lag between them. So say for example, when you are applying a voltage channel, your current channel might be lagging behind or leading ahead. So in that case what will happen is, your oscilloscope will measure 2 different waveforms which are shifted from each other in time frame, and you don't want that, right? So for that there's a calibration step called de-skewing. So this is basically a calibration substrate I'm showing, and I'll tell you the more geometric details of this calibration setup. The second calibration step involves a voltage channel calibration. So in your whole TLP setup, when I was showing you 2 different set of lines, right? One was coming from the TLP generator to the device under test, and the other line was going from your device under test to the oscilloscope. Now these 2 lines also involve a lot of wires, right? These wires, or the components that are involved in them, might also have a lot of impedances, and that's why it's important to actually calibrate the 2 lines as well. Now the calibration of the voltage channel line is done through a Zener diode, and the calibration of the other line is done through a diode and through a resistor. Also they are calibrated using a set of open pads as well, where the calibration of the voltage channel is then done through an open pad and a Zener diode. So what happens is, when you have these open pads, you would not expect any current to come through the device, right? And then you would have a voltage signal only being captured at your oscilloscope. So if there is any difference and if there is a current between the devices, you would know that the resistor divider network that we showed earlier is also passing current, and that's what you don't want. Secondly, the Zener diode is important because, as you know, Zener diode has a very set turn on voltage, and you know so in this calibration substrate are different Zener diodes, the turn on voltage of which you accurately know. So when you measure the turn on voltage and then you have the actual turn on voltage, by comparing these two, you can actually measure how much attenuation is happening at the voltage channel. Finally, the current channel is calibrated through a resistor that's here in the calibration substrate. These resistors also have a certain actual resistance, and then you have a measured resistance in them, and by comparing these two, you can actually measure the current factor as well. So that's why this calibration is important. It's a pretty involved process as well, and I'll talk about it in further detail, and I'll show you the steps involving the calibration steps once we start doing the experimental measurements. So whenever you're trying to do a measurement, it's important that you do the calibration. Now the general practice is that whenever you change the rise time of the measurement, so you have freedom in terms of adjusting the pulse width as well as the rise time of the signal that you're going to apply. So whenever you change the rise time of this whole setup, and you're going to shift from 10 nanosecond to 1 nanosecond rise time, you would have to do the calibration again. Secondly, if you know that a lot of time has passed and your setup has changed in terms of space, then it's always a good practice to do the calibration all over again. But if you're going to do a couple of measurements one after other, say in a 6-hour, 10-hour time frame, then it's okay to actually do calibration once and then use the calibration parameters throughout your measurement. But wherever there is a difference, there's a special movement of transmission lines, or any important factor has changed in your measurement, you will have to do the calibration all over again. So now that I've shown you different components that are involved in a TLP setup, let me take a few minutes and discuss how these components then talk to each other. So one set of communication lines is established through this GPIB probe tip, GPIB connections. So that means the TLP generator, oscilloscope, the controlling system, and some other components involving the SMUs as well, communicate between each other through different GPIB connections. So these GPIB connections act as the communication lines. So basically these components keep telling each other that who is active at what time and what has to be done at different time periods. And these are all controlled through the host PC. So the host PC basically tells the TLP generator or the oscilloscope or the SMU here that you have to get involved at this point. Okay, and then they have GPIB lines between them as well. Now between the oscilloscope and the generator, pulse generator here, there is also a trigger line. Now this trigger line is important because the TLP generator also has to tell the oscilloscope that it's time for you to do the measurement. So this trigger line then, so the trigger line between these two have a voltage signal that is passed. In our case, we have set the oscilloscope in such a way that whenever the oscilloscope measures a rising edge, so say for example if this is the signal, the trigger signal, and whenever you have this rising edge of the trigger signal here, that's when the oscilloscope gets triggered and the oscilloscope gets ready to do the measurements. So this is how the TLP generator and the oscilloscope talk to each other. So all these components then, so the communication line involves either a GPIB or a trigger network between different components. So now that I've talked about the components in some detail, I've told you about different components and what they do. You can always find find more information in the web as well. So I'll now discuss a little bit of a physical background of the TLP generator and how the pulse transmission takes place. So let's just plot voltage as a function of time, and I'll show you different how the voltage signal changes at different time periods, and I was talking about the incident and the reflected waves, and I'm sorry about the bad handwriting. So let's say at t is equals to 0 here, your TLP generator generates a TLP pulse of some time period, right? Now this TLP generator, this pulse would then reach the switch. So say for example, if the velocity of this pulse is v, and the length and the distance between the transmission generator and the switch here is, and I'm taking some liberty to actually plot spatial directions as well, and I'm so say if the velocity of the pulse is v and the distance between your generator and the switch is L, your switch will have these lines, switch will have this waveforms at a time period t is equals to L by V. Now once the switch has turned on and you have this transmission line network connected ahead as well, you would have some pulse, some input wave that is getting reflected back, and some that is then incident upon the whole network. This incident wave will then go to your DUT as well. Okay, so let's say, so again, say for example, switch to the DUT is then say L2. Then you have a time period T equal to L plus L2 by V, where the DUT will have this pulse that is getting applied to it. Now the important thing here is, because everything has a 50 ohm characteristic impedance. So say for example, if the amplitude of this pulse is V1, the incident and the reflected waves both have a same impedance. So this impedance, so this voltage waveform would be V1 by 2, and the reflected wave will also have a amplitude of V1 by 2. At t is equals to say L plus L2 by V, your reflected wave will also have come back by that much distance from your switch, L2. Okay. So at any point of time you would have these reflected waves and as well as the incident waves. At some other time period, that would be, well, just at the time period t is equals to L plus 2L2 by V, basically your DUT would also have reflected some voltage waveforms, and these voltage waveforms then would have come back again to the switch here. And if this 2L2 is greater than L, your reflected wave here would have diminished. So basically you will have another incident wave coming, and this reflected wave would have diminished by now, and your reflected wave from the DUT would then go to the switch again, from where it will go to the oscilloscope. Now the interesting thing to note here is that the time constant of the whole setup are decided by the length of the transmission lines at different points of time. So basically your switch to DUT transmission line length L2, your transmission line to the switch transmission line length L, have an important role to play in the pulse width that you can apply and the time period that's get involved in the whole TLP measurements. And that's why it's always a good practice to keep the switch and the distance between the DUT as close as possible, the distance between the pulse generator and the switch as close as possible, so that you have more freedom in terms of pulses that you can apply. So for example, if say this time period from the DUT to the switch back is more than 100 nanosecond, or more, say it's 1000 nanoseconds, what will happen is, by the time the DUT reflects this line signal back to the switch, more incident waves would have been generated, and then it would interfere with the whole measurement setup as well. So basically you would like to optimize these lengths in some way, so that you have a lot of flexibility in the time periods that you can get involved in. So yeah, so this is one so this is an important physical understanding to have as regards to the TLP setup. Now a couple of things to take care of. So when I was talking about your TLP setup, and I was talking, if you remember in the very start, I was talking about these different models, HBM, CDM, MM as well. An important thing to notice is, an important thing to know here is, all these different waveforms, all these different models also have different waveforms, which are somewhat different from TLP generator. So then again, this is say time versus the current. Your HBM has a waveform somewhere like this, a decaying waveform roughly rectangular in shape, but a decaying waveform. Your machine model has a very impulse-like waveform here, something like this, which does not have a time period of more than a few nanoseconds. HBM has a time period of 150 nanoseconds. Sorry about that, 150 nanoseconds. And then you also have a CDM pulse, which is oscillatory in nature but decaying as well. Your TLP generator, on the other hand, as I was telling you, has a more rectangular waveform. So it's like this. Now, as you can see, it's different from all other waveforms in some sense, and that's because these waveforms are more random in nature, and it's very difficult to actually experimentally generate these different waveforms with pinpoint accuracy. So that's why you go with a rectangular waveform as well. So the important thing is, by changing the pulse width of the TLP generator, you could emulate to some extent different ESD models. HBM is more easier to do it because HBM also has a somewhat of a rectangular shape, although it's decaying in nature, but it has a somewhat somewhat similar shapes. So the amount of heating that is involved, amount of power dissipated that is being involved between the TLP and HBM are somewhat similar. This is, however, not the case in other models. TLP CDM or TLP MM have a higher mismatch as regards to power delivery that is being happening to the device under test. And as you know, the more heat you apply to a device, if you apply different heats at different measurements, the probability of the device getting damaged becomes different. So that's why you also have a lot of correlation issues as well. These correlation issues then depend upon the technology that you're talking about, the device you're talking about. So say for example, if your device does not have any thermal component in it, device failure does not have any thermal component in it, you would see a much lower impact of the heating component involved and the power dissipated. However, if it is completely thermal in nature, then you would see a very different signal altogether. So yeah, so this correlation is something that you would have to take care of for different technologies, and you would see a lot of literature on this as well with regards to different technologies. So yeah, so that is one thing that you have to understand as well, that when you are doing a TLP measurements, there is some amount of mismatch between the other experimental measurements, other ESD qualifications. The importance of the TLP network comes into picture because it gives you a more physical picture of how the device is getting failed. So all these other measurement techniques, CDM, MM and HBM, only give you a ESD qualification vis-a-vis your device under test, and they just tell you whether the device has passed this much level of qualification or not. So say for example, if you design a MOSFET which is supposed to stand at 2 kilovolts, your HBM and your CDM would only tell you whether the device is passing that level of voltage test or not. Your TLP, on the other hand, because of the voltage signal that you are applying, gives you much more intuitive and actually physically important information as well. So that's why TLP is preferred in some senses also, but then you will also have to take care of these correlation issues. And now one point that I missed here was to show you how the TLP pulses are applied. Sorry about that as well. Yeah, your TLP pulses so basically the voltage pulses that you apply, while you can actually keep the amplitude constant, generally for a new device or for a new set of measurements, you always have this step kind of an signal. So for example, if this is a pulse, say of 5 volts, 100 nanoseconds, you would have this off time. Now this off time, and I'll show you in the measurements in the other video as well, is very high compared to the on time. So say for example, this on time is, if it is 100 nanosecond, the off time would easily be in the range of milliseconds. This is important because during this 100 nanoseconds, when you're applying this very high pulse, a lot of power is also dissipated in your device. And what you want is that when the next signal is applied, your device is free from any influence of this voltage pulse. So say for example, if after a 5 volt signal I apply a 10 volt signal, you don't want any residual effect from this 5 volt signal coming into the measurement here. And for that reason, it's important to keep a very high off time. Now the TLP pulses, coming back to the TLP pulses, they are applied in a step fashion. So say for example, from 5 volt you will go to 10 volts, you would apply a T off again, and then you would apply a 15 volt signal. The good thing about this measurement setup is then that you know the device operation and device behavior at different voltage levels. So say for example, if I'm using a particular device and my device fails at say 100 volt, but before that, if your device is degrading in performance, it's not completely damaged, but it's degrading, you would start seeing the signals of that degradation at different voltage levels, and that becomes very important when you're discussing the physics of the device operation, because device failure may or may not take place in an instant. It may be gradual in nature over different voltage pulses, and that's important to know, because then your device, when you're applying an instant, might actually go beyond 2 kilovolt signals, because there's no soft damage that is taking place over a period of time. And you would see in a lot of reliability techniques that this damage that happens and looks instantaneous is not actually instantaneous, it's more gradual in nature as well, and that's a very high, that has a very high instance in dielectric breakdown as well. So yeah, so this is how the voltage signals are applied in your TLP generator, and that's why the TLP offers more physical information compared to other characterization techniques of involving HBM, CD and MM. While it may not give you the correct qualification values, it gives you a lot of more information about the physics of the device operation. I was also, if you remember, I was also talking about these SMU and applying a low voltage bias in the off time. So what happens is, now that I'm discussing this, I'll discuss this as well. When you have applied a voltage pulse to the device through a TLP generator, now this off time that you have is a very high off time. And why waste this off time, right? So what you do is you apply a very low voltage DC bias to the device under test. So the DC bias is generally in the range of a few volts. You could actually keep it in millivolts as well, and I personally prefer it to keep it at 0.5 volts for my devices. So what I do is I'll measure the current at 0.5 volt here, I'll measure the current at 0.5 volt here, and this leakage measurement also gives me a lot of information how the device is changing. So say for example, if it's conducting 1 nanoampere current here and it starts to conduct 1 picoampere of current here, I know something has happened to my device in this voltage waveform, in this voltage signal, that has led to this change all of a sudden. So that's why this leakage test is important, and that's the importance, that shows you the importance of switch as well, because the switch is the component that is going to alternate between these two measurements every time. It's also going to measure the signal as pulse signal as well. It has a role in measuring the pulse output from the DUT through to the oscilloscope. It also has a role here as well. So that's why switch is one of the major components in the TLP setup. Now one final thing that I'll discuss today is averaging. So when you start reading, in this whole in this whole video so far, I've been talking about the current and the voltage waveforms, and that you capture the current and the voltage waveforms of device under test at different times and whatnot. However, when you start reading your ESD literature for the first time, you would see, not waveforms in particular, you would see a lot of IV characteristic which look like this, or which may have any weird, which may have any shape possible for different devices. But you would see a lot of IV characteristics called the TLP IV characteristic. Where do these come from? Now these come from a very interesting thing that we do. Whenever you capture a voltage and the current waveform, so this can be V or I as a function of time, and this is oscilloscope measurements. Whenever you capture a voltage or say a current waveform, the current waveform could look like this. You could choose actually any weird shape if you want. I'll just keep it here. Let's not have the current lagging, current leading the voltage. Yeah, so this is your current and this is your voltage. So this is what your oscilloscope captures. This is the information that you also get from TLP. However, this information, while it shows some things, it also misses some things as well. So what we do is, to create an IV characteristic, we actually average out the voltage values here in this time frame. You could ideally decide what time frame you want, we generally keep it at 60 to 80% of the voltage waveform. So say for example, if the voltage pulse width is 100 nanosecond, from 60 nanosecond to 80 nanoseconds, I would measure these values, I would have these values measured, right? And I would then average out the value, V1 plus V2 plus all these things divided by the number of instances that I am measuring. So say for example, if this is 10 and these are 10 different values, I would get a V average value. Similarly for the current in the same time frame, you will capture these different values here, 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 and you would average out the current. These averaged values are then used to construct a TLP IV characteristic that you would see a lot in literature. So every point, so say for example, if the voltage here is 5 volts average, you would have this 5 average and a current value coming. For every voltage waveform, you would do the same. So you have different values coming from different voltage ranges, and that's how you construct a TLP IV characteristic, quasi-static characteristic, that you would see a lot of literature as well. And that's important because this characteristic gives you a lot of broad information about the device under test. You can actually show your device degrading, your device saturating, your device having a higher current over different voltage ranges. So this quasi-static IV characteristic gives you a lot of information about the device under test as well, and that's actually very important. It also gives you a lot of broad range information. Instead of going into the very specifics of the voltage waveforms every now and then, you can actually broaden this up and show the whole range of information in one shot, and that's why this averaging is important. Now one thing to notice is, when I was talking about averaging, I talked about the averaging in the later half of the voltage waveform, 60 to 80%, 70 to 90, whatever you like. Why did I do that? Now the reason I did that is, if you have noticed so far, the voltage waveforms that we are talking about are rectangular in nature, right? And while I am showing you this as a straight line, as a perfectly balanced signal, it may not be so. It may have some ringing effect here and there. You would have some ringing effect, you would have some effects initially. Basically, when you are applying a very high voltage pulse to anything, you would have some overshoots as well. So you would have some overshoot here, some undershoots. Now the 60 to 80% is actually the time period, or 70 to 90% is the time period your voltage waveform has actually settled down. So basically all these parasitic components of the wires, of the cables, have all settled down by this time period. So the voltage that you are going to use or the measure is going to be the actual device free of any parasitic impedances. And that's the reason why we use the 60 to 80% or 70 to 90% as the averaging window for both the current and the voltage, so that you don't capture the parasitics, you capture only the DUT behavior. Yeah. So that's why the averaging part is also important. It gives you a lot of information. Voltage waveforms also give you a lot of information, but yeah, constructing this quasi-static IV characteristic is kind of having a bird's eye view in some senses. Yeah, so that's why it's important, and it's an important information to have in your TLP setup. Now in today's lecture, I've talked a lot about the theoretical part. I showed you different components, I showed you what ESD is, what TLP is, and I'll show you some information about that voltage waveforms with respect to time. I talked about TLP averaging, and I showed you the whole setup in a more theoretical sense. In the next lecture, I'll talk more about the experimental nature. I'll show you some measurements, I'll show you the calibration as well, and I'll show you different steps and softwares that are involved in actually processing the data, understanding the data, and capturing and measuring the data as well. So thanks.